Hello everyone, welcome to the 2024 Term 2 MATH3311 / MATH5335 revision seminar brought to you by UNSW MathSoc and UNSW QuantSoc. I'm Ehhrm and I'll be presenting part 1 of the seminar today, and tomorrow at the same time Helen will be presenting part 2. Okay, so today for part 1, these are the topics that we will go through. So that's everything up to and including Fourier analysis and fast Fourier transform. So this will also cover most of questions 1 and 2 in the final paper, not including numerical integration and Taylor series, I think, but all the other questions should fall under one of these topics. Okay, let's start. So the first topic is computing with real numbers, and this topic is basically about how computers store numbers and how they work with numbers. So how computers store numbers is they store them in this form, as I think most people will be familiar with. This has come up in I think this was in the first assignment. Okay, so basically it's got a few bits representing the number, a few bits representing the exponent, and 1 bit for the sign. And in 64-bit machines, we usually have 52 for this part, 11 bits for E, and then 1 for the sign. Okay, next is the idea of machine epsilon. So machine epsilon is the difference between 1 and the next number after 1 on the computer. So in 64-bit machines, it's 10 to the minus 16, a value that we've used a lot throughout the course. But for different machines, this is not always the case, as we'll see in our first example question. So here is a much simpler case. So there's only 1, 2, 3, 4 bits, and part A wants us to write down all the numbers that can be represented with these bits. So what we can do here is just list all of them out. So the -1 to the power of s, this just means every number we can make, we can also make the negative version of that number. So let's list out what this part can represent first. So this can be 1.00, 1.01, 1.10, and 1.11. And this gets multiplied to 2 to the power of e, 2 to the power of either 0 or 1. So this can be either multiplied by 1 or by 2. And because of this first bit, we can take plus minus. So the next thing we have to do is translate these representations into actual numbers. So 1.00, that's just 1. So this first bit represents 1, the next one is 0.5, and then the next one is 0.25. So here we have 1.25, 1.5, and then 1.75. And we'll be taking plus minus in all of these. And then we multiply by 2 for this. So and these are all the numbers that can be represented using this representation. C and D ask what's the real max and what's the real min. Real max is the largest number that can be represented, so that would be 3.5. And real min is the smallest, I think it's the smallest positive number that can be represented. And here that would be 1. And machine epsilon here. So epsilon is the difference between 1 and the next number after 1. So that would be the difference between 1 and 1.25. So machine epsilon here will be 0.25. And this has been emphasized in the labs and lectures, but this difference is not the same as the difference between 2 and the next number after 2. So here that would be 0.5, whereas machine epsilon is 0.25. Okay, so the next slide is about flops. So a flop or floating point operation is one of the basic operations applied to floating point numbers. It's useful to talk about flops because we can use flops to estimate the time a calculation or a calculation or a task will take. So we can do that by calculating the speed at which the machine can process flops with this formula. So we can multiply all of these together and then we get the speed. Then we can use the speed to estimate the time. So that's exactly what we're required to do in this question. So here we're only looking at parts B and C of this question. Part A is about memory, which is not relevant to the next 2 parts. So the part B, so this is part B and this is part C. Part B wants us to estimate the number of flops that are required to compute this Cholesky factorization. The problem here is we don't know what C is. We just know it's some constant, but since n is so large and we only want an estimate, we can just ignore the n squared term because the n cubed term will be so large. So here we estimate the number of flops to be 10 to the power of 3 to the power of 3 over 3, which is 3.33 times 10 to the power of 8, I think. Okay, I think it is 10 to the power of 8. Part C wants us to estimate how long this calculation will take. So first, we want to calculate the speed in flops per second using this formula. So the clock here is 4 gigahertz, So the speed is 4 times 10 to the 9 times the number of cores, which is 4, times the speed. So the speed in flops per cycle. So this is 1 flop per cycle. So we end up with a speed of 1.6 times 10 to the 10. And then how long the task will take, we can just take the number of flops divided by the speed. So 3.33 times 10 to the 8 over 1.6 times 10 to the 10. So this will approximately be 2 times 10 to the minus 2, or 0.02 seconds. So, okay, now we move on to topic 2, which is about norms and sensitivity. So at the end of this topic, this topic basically builds up to seeing what we can say about the numerical stability of a linear system AX is equal to B. So we'll start by introducing vector norms, which I think most people will be familiar with by now, but if not, then here's a recap. So then this idea of norms gets applied to matrices. So matrix norms also satisfy the norm properties. So these are the norm properties, but there's an extra thing for matrix norms that can be true. So if we have this property, then the matrix norm is said to be consistent. Okay. But in practice for the course, there's only a few matrix norms that are actually important. So the two kind of general classes are the P norms, which are defined like this, and the Frobenius norm, which is like squaring every entry in the matrix, summing them, and then taking the square root. So treating the matrix as a vector with m by n elements, and then taking the 2 norm of that. But usually in the questions from the past papers, I think there's more to do with norms of this type, and there's only 3 special cases of the P norm that get used in this course, and that's these 3. The 1 norm, which is the max column sum, and the infinity norm, which is the max row sum. Personally, I find it quite hard to remember which one's which. So in the piece of paper we can bring into the final, I would write something that's just like remind myself. Okay. Then there's also the matrix 2 norm, which is quite which is calculated quite differently. So the matrix 2 norm is the square root of the largest eigenvalue of A transpose A. Okay, now we do a past question with matrix norms. So this exact question has popped up in a lot of the different papers, and it's always like it's the same question with slightly different variations. So it either asks part C or part D, and here we do the 2018 question and the 2019 question. So that's so part C will be 2018 and part D is 2019, I think. Okay, so part A, what property must Q satisfy to be an orthogonal matrix? So orthogonal just means the transpose is the inverse. B wants us to state the definition of the subordinate 2 norm. So we have the 2 norm of Q is max over non-zero x of the 2 norm of the vector qx over the 2 norm of the vector x. And now part C wants us to show that if Q is orthogonal, then the 2 norm is 1. 2 norm of Q is 1. So if we, okay, that should be 2. So if we look here, we can write the top as X transpose Q transpose times QX square root of that. And then since Q is orthogonal, Q transpose Q just becomes the identity. So what we have is the X transpose X square root of X transpose X over the 2 norm of X. And we know that's just the 2 norm of X. So this is always equal to 1, which means the max over non-zero x is also 1. So that means the 2 norm will always be 1. Part D, so in the 2019 paper, they don't get you to do C first, I think. So we can't use the result of part C, but basically it's the same thing. If Q is orthogonal, then the inverse is also orthogonal. So we can go through the same process as here to show that the 2 norm of that matrix is 1. So after norms get introduced, there's also the idea of condition numbers. So first, let's review what it means for a matrix to be non-singular. So a square matrix is non-singular if it's invertible. So that means the determinant is not 0. And that's the same as if all eigenvalues are non-zero. And so for non-singular matrices, the condition number is defined like this. So it's the matrix norm of A times the matrix norm of A inverse. And here it doesn't matter which norm gets used, as long as these two are the same norm. And here we need non-singular because we're taking the inverse of A. Here are some properties of condition numbers. The first two are quite easy to see. The third one applies to real symmetric matrices. And the 2 norm, so it gives us a way to find the 2 norms, in the 2 norm condition number in terms of the eigenvalues. So the 2 norm addition number will be the max eigenvalue over the least eigenvalue. And the fourth property just says a matrix with a larger addition number it's less numerically stable to solve. And we say that it's ill-conditioned if the condition number is larger than 1 over epsilon. Okay, so the point of introducing condition numbers is to talk about the sensitivity of linear systems. So if we have a linear system, AX is equal to B, and we know A and B, we want to know how confident we can be in our X that we find. So here we have the approximation that the relative error in X, which is the error in X over the size of X, I think. So that's the relative error of X. That is less than the condition number times the sum of the relative errors of A and B. And here the next block is just translating significant figures to relative error. Okay, so here we have an example problem from the 2013 paper that wants us to work with this to say something about how precise we need the information of a linear system to be. So this is just part E. In part D, it asks us to find this from some MATLAB outputs. And part E wants us to solve this question. So we have a system Cx is equal to B. And we want our computed solution to have at least 4 significant figures, which means we want the relative error in X to be less than or equal to 0.5 times 10 to the minus 4. And the question asks, how accurate do we need B to be? So using this formula we have here, we have rho of X is less than kappa of C times rho of C plus rho of B. So if we want to guarantee that this line holds, we can just make this thing less than what we get here. So we can just try to solve the inequality 0.5 times 10 to the minus 4 is less than or equal to this. Okay, so the next important bit is that the elements of C are known exactly, but this is a computer, so exactly just means the error is less than the machine precision. So I think normally we assume we're working in 64-bit, so the relative error of C would be 10 to the minus 16. So then we sub in all the values and we get this. This is less than 5 times 10 to the 9 times that. Now we just want to rearrange for row of B. So this term is quite small compared to everything else, so we can just assume that it's close to 0. Then we get row of B should be oh wait, I think I might have made a mistake in my calculations. And I have the inequality. No, I have the inequality the wrong way around. Yes, so we want it to be this way, so we have an upper bound for the error. So row of B should be less than 2.5 times 10 to the minus 4 over 5 times 10 to the 9. And this would be 0.1 times 10 to the minus 13. So, and that's less than 0.5 times 10 to the power of minus 14. So we have to know row of B to 14 significant figures to achieve this degree of accuracy in our solution. Okay. Topic 3 is about matrix structures and factorizations. So in this seminar we'll do more of factorizations because that's where most of the exam questions are. But first we'll revise some content from matrix structures. So covariance and correlation matrices. So covariance matrices have this form, which means they are symmetric and they are positive semi-definite. So these are the two important properties of covariance matrices. And the correlation matrices are defined like this, which follows from the normal definition of correlation. Positive definiteness. This is a property of matrices, and a matrix is positive definite if for any non-zero x, x transpose ax is larger than 0. So here we define positive definite and positive semi-definite, but negative definite is defined in the same way, just the inequality here is reversed. And a special case in real symmetric matrices, we can say stuff about we can say things about if a matrix is positive definite based on its eigenvalues. So we know that all the eigenvalues are real. If they are also all positive, then A is positive definite. And similarly for all the other definites. Okay, now we have an example question from 2016. So we have a matrix B that's expressed like this, and part A wants us to show that B is positive definite. So here, we can just use the first block, the definition. So we want to show that for any non-zero x, we have x transpose bx is larger than 0. So if we calculate that, we find x transpose b of x is equal to x transpose I times x plus the sum of x transpose v and then v transpose x, which we can also write as the 2 norm of x squared plus the sum of so once we do this multiplication, that becomes a scalar, and these two become these two are the same thing, because when we're taking dot products, the order doesn't matter for real vectors. So we can say that it's this squared. And we see that x transpose bx is just the sum of a bunch of positive numbers. So this must be strictly larger than 0. We don't have the equality here because x is non-zero, so this will also be larger than 0. Okay, the next property is diagonal dominance. So this actually hasn't been tested in any of the past papers, but it's part of the content, so we'll briefly go through it. So what this basically means is that if every diagonal entry is larger than the absolute sum of the rest of its row, so every diagonal entry is larger than the rest of its row added together. And there's a relationship with positive definiteness here. So in symmetric matrices, strict diagonal dominance implies positive definiteness, but we don't have a converse relation there. Okay, now we move on to factorizations. So there's 5 types of factorizations covered in the course, these 5. And we'll start with LU factorization. So this is a factorization of a matrix into a unit lower triangular matrix and an upper triangular matrix. And this can be done, so we might end up with pivoting here with a permutation matrix P. What this is useful for is it gives us a more computationally efficient way of solving linear systems. So as an example, we have question 1I from 2019. So part A wants us to write down the LU factorization with pivoting. So here we have PA is equal to LU, where P is permutation matrix, L is unit lower triangular, and U is upper triangle. Now we want an efficient way of solving large linear systems. So the process here is to use this LU factorization. So we want to solve AXK is equal to BK. We can multiply P to both sides, I think. Okay, looks like we're back. Sorry, my internet briefly got cut out. So here, after multiplying P to the left side, we have PA is equal to LU. So we can write this equation like this. Actually here we don't even need to work with the BK yet. So it's just expressing PA times XK in terms of the LU factorization. And here we use AXK is equal to BK to bring BK back into this equation. Then what we have is just a linear system with triangular matrices that we can solve. So here the steps will be first write it like this, and then we would solve Ly is equal to PBK using forward substitution. And then we would solve UXK is equal to YK using back substitution. So this will be forward. And then okay. And part C wants us to calculate the cost of solving these systems. So computing the LU factorization costs 2 over 3 n to the 3 flops. So that's a cost we can't avoid. So we'll have 2 over 3 n to the 3. And computing one forward-backward substitution costs n squared flops. So we have an n by n matrix. Each of these steps requires us to do n forward-backward substitutions. So I think we get 2n cubed substitutions in total. So it will be 2n times n squared flops in total for these substitutions. And then we add those together and we get 8 over 3 n cubed substitutions. Let me check with the answers just to make sure that's actually right. Okay, no, it's not n here, so it turns out I have actually made a mistake here. It's not n. The number of substitutions we have to do is actually k, where k is the number of equations we have. So this would be 2kn squared. And that will get us the answer. Okay, next factorization is Cholesky factorization. So this is decomposing a symmetric positive definite matrix into an upper triangular matrix, the transpose of it times itself. And the existence of Cholesky factorization implies that the matrix is positive and definite. Then next one is QR factorization. So Q here is orthogonal and R is the upper triangular. And we have an example question from 2018 for this. So part A is just the properties here. Q is orthogonal and R is upper triangular. Part B, so we have found the QR decomposition of A. So we have A is QR. And we want to compute this efficiently. So what we can do here is write A as QR. So we have B transpose, R transpose, QRB. So this is equal to this. Since Q is orthogonal, we have B transpose, RB, which is just the 2 norm of RB squared. So the most efficient way of computing this is to 1, compute RB, and then to take the 2 norm. find the square of the 2 norm. Part C is quite similar, but now we want to work with the inverse of A transpose A. Again, it's the same idea, just replacing A with QR. So we have this is equal to this, and then the orthogonal matrices cancel out. So we have this, and then we can write the middle bit as C transpose R inverse R transpose inverse C, and this is the squared 2 norm of inverse of R transpose T times C. But the problem is we don't want to explicitly calculate the inverse of R transpose. So what we can do is, since R is triangular, we can quite efficiently solve the linear system R transpose X is equal to C. So the first step will be to solve this, and then take the squared 2 norm of X. So we don't explicitly find the inverse of this, rather we want to just find the whole thing by solving a linear system. Okay. The next factorization is the singular value decomposition, so that decomposes A into 2 orthogonal matrices and a diagonal with extra zeros, with its singular values. So the singular values can be used to define the condition number for non-square matrices, and this is how it's defined. So we arrange the singular values in descending order. So we have the largest one over the smallest one. And that's what we define as the 2 norm condition number. So if we scroll up to the condition number parts, that's kind of similar to what we did here. Expressing that in terms of the eigenvalues, but now it's in terms of the singular values. Okay, and we have an example question from the 2017 paper. So part A wants us to write down the SVD and state the properties of the matrices. So here it also wants the dimensions of the matrices. So A is n by n, which means, so A is equal to U. So U will be m by m. This will be m by n, and V transpose will be n by n. U and V will be orthogonal, and and the middle matrix will be as defined here. Now we have all of these singular values, and we want an approximation of the matrix A using just the 10 largest singular values. So what we can do is ignore all of the singular values after 10 and basically set them to 0. And then multiply the matrices together. With a changed middle matrix. So I think what we do here is actually like cut out the entries from U and V2 that will turn into 0 when multiplied to this reduced version. So we want to have, we define a new sigma as a 10 by 10 diagonal matrix with the 10 largest singular values on the diagonal. Then U, cut down U so that it's m by 10, and cut down Vt so that it's 10 by n. Then we have the approximation. A is approximately given by this multiplication. Okay, and now part C wants us to find how much memory it takes to store this approximation. So matrix A has m by n elements, and that requires 8 mn bytes. So we can assume that one element takes 8 bytes. To store. So to store U, this is m by 10. So that will take up m times 10 times 8 bytes. To store sigma, we actually just need to store the singular values here. So this will be 10 times 8 bytes. And then to store V, it should be V transpose here. It will be 10 times n times 8 bytes. So in total, we need 80 m plus n plus 80 bytes. So this example shows an application of the SVD to approximate large matrices, making them smaller to store while still preserving like the most important bits of information. And the last one, I haven't seen many questions involving this, but this is the spectral or eigenvalue decomposition. So it decomposes A into a diagonal matrix with the eigenvalue values on the diagonal, and an orthogonal matrix V. Okay, that's the end of topic 3. Now topic 4 is data fitting. This topic I actually haven't seen tested much in the past papers. I could only find like a few questions, and they're all kind of like this. I think that's because it's been tested quite a lot in the assignments and the lab test, and also it'll be pretty tedious to do the data fitting by hand in the exam. So the example question I have here is from the 2017 paper, and it's about polynomial interpolation, and this is a more qualitative problem. So part A wants us to find the degree of the polynomial, so that it can pass through every single one of these data points. So here we have 9 pieces of information, so that means we need 9 predictors in our model. So those 9 predictors would be 1, x squared, and so on. And since we need 9 of them, our last term should be x to the 8. So our polynomial will be degree 8. And part B asks, is using a polynomial a good idea? And give reasons for your answer. So the problem with polynomials with high degrees is that it will go like up and down a lot, even though it passes through the data points perfectly. So it's not very useful for estimating values that aren't. It's not useful for estimating values between data points. So with a polynomial of such high degree, this is not a good idea. And a better choice will be like a lower degree of polynomial or a spline. So that's all I had for the data fitting. Now we'll move on to topic 5, so splines and sparse matrices. Let's start with splines. So splines are basically, you have a bunch of data points, and then you get polynomials that fit between each pair of data points and kind of glue them all together. Then here, this second part is matching the derivatives, so you still have a smooth curve. The type of splines we use the most in the course are cubic splines, so part 2 will just be matching the first 2 derivatives. And there's a bunch of different types of splines. There's the natural spline, clamped spline, and not spline. So these just impose different conditions on the endpoints, or like the relationship between points. So these change how the splines will look and behave. Okay, we have an example question from 2023. So we have a cubic spline, a natural cubic spline on 0, 2. So we have 3 points here, 0, 1, and 2. And we want to solve for all of these coefficients. Okay, so the information we have is that first it's a cubic spline, so the values at the connecting points should match, and this first two derivatives should also match at they should also match at the endpoints. And the last piece of information we have is that it's a natural spline, so we have this condition. The hint in the question tells us to use this first to find A, so that's probably a good place to start. So S1. The second derivative of this will be minus 2a plus 6bx. And then S1 of 0 would be minus 2a, which is equal to 0. So we have a is equal to 0 here. So that means we can also write S1 is equal to 1 plus x plus bx cubed. Now we can start matching the endpoints. So at x is equal to 1, we have 1 plus b, which is 2 plus b, and S2 of 1 is c plus minus 1 to the power of 3, which is c minus 1. And we can also match the derivatives. So differentiating this, we get 1 plus 3bx squared, and for S2 we have this. So here we still don't have enough information to solve for B, C, or D. So let's also match the second derivatives. So here that would be 6x minus 2. So matching the second derivatives at 1, we get 6b, and S2, that will be minus 6. So that implies b is minus 1. So once we know b is minus 1, then we have 2 plus b is equal to c minus 1. So 1 is equal to c minus 1, and c is equal to 2. And here we have 1 plus 3b is equal to d plus 3. So here we get 1 plus 3b is equal to d plus 3. So minus 2 is equal to d plus 3, so d is minus 5. So our final answer will be A is 0, B is -1, C is 2, and D is -5. Okay, so the key idea of this question was just taking all the information that we have about splines and then forming equations with those to solve for these coefficients. Okay, the next topic is sparse matrices. So a sparse matrix is a matrix where its 0 elements can be exploited to improve efficiency. In the past papers, when I read through the solutions, I found that the course is quite loose with the 0 elements part. So matrices like matrices like this were also considered sparse, even though if you actually calculate this is not guaranteed to have many 0 entries. But I think that's the idea of hidden sparsity here. So matrices may possess hidden sparsity. So for example, something like this where B is a lot easier to store than A. It's generally dense, so if you actually expand this out, there's no guarantee that it's sparse, but its structure can still be exploited to make A easier to work with. So I think any matrix where you can kind of exploit this structure can be called sparse. And the example we have is this one. So this is from 2017. So we have a matrix D that's written like this. So a lower triangular matrix plus some 2 column vectors U V transpose. Part A asks, why is explicitly forming this matrix not a good idea? That's because right now it's pretty easy to store. So for B, it's just a lower triangular, and every element is also the same. And U and V are also a lot less expensive to store compared to a full n by n matrix. So I think the justification in the answers was that currently it has a simple structure and it's sparse. And explicitly forming D ruins both of these properties. Okay, part B now actually wants us to exploit this structure to make a computation more efficient. So we want to compute dz for some given vector z. So we can write that as bz plus uv transpose z. And it wants us to count the number of additions and multiplications we need. So let's deal with the second part first. This is the easier part. So v transpose z, we're doing n multiplications and also n minus 1 additions. And after we have that, so that becomes a scalar. So if we want to compute V transpose Z times U, then that's also n multiplications, just multiplying that to every element of U. So for UVZ, UV transpose Z, we have 2n multiplications and n minus 1 additions. Now to compute BZ, there's quite a clever trick that can be used, and that relies on the lower triangular structure of B, as well as the fact that every entry is 1. So if you compute BZ, that becomes Z1, Z1 plus Z2, Z1 plus Z2 plus Z3, and so on. An algorithm that can be used to compute this efficiently is just say if we let BZ equal to Y, then you can set Y1 is equal to Z1, Y2 is Z2 plus Z1, Z2 plus Y1 actually. And then Y3 is Z3 plus Y2 and so on. So you can kind of recursively calculate BZY here. And this only costs n minus 1 additions. Because for the first term, there's no flops involved as well. So calculating BZ only requires n minus 1 additions. Now, finally combining the two together, these will be vectors in Rn, so there will be n additions to add everything together. So final addition, there will be n addition operations. So in total, to calculate DZ, we need 2n multiplications and then n minus 1 plus n minus 1 plus n, which is 3n minus 2 additions. So this is an example of a sparse matrix question that has popped up in quite a few variants in the past papers. So the main idea, I guess, here is to justify why explicitly forming the matrix is not a good idea, and then finding a way to exploit the matrix's structure to make computations easier. Okay, now our last topic for this first half of the seminar is Fourier and analysis and the fast Fourier transform. But we will actually focus more on the discrete Fourier transform, because I think every single past paper question we've had on this topic has been about some kind of the discrete Fourier transform. Okay, so the overview. The discrete Fourier transform takes a bunch of data and extracts the periodic components. So, for example, here we have this data, and once we put that through the discrete Fourier transform, it gives us these spikes where there's like a periodic component. So here there's a periodic component of 1 cycle per year and also 12 cycles per year. So this is kind of analogous to in music. If you hear a chord, decomposing that into the individual notes the chord is made up of. So again, as we said earlier, we will focus mostly on the discrete Fourier transform here. So this is the formula for the discrete Fourier transform. So after we've computed that, we can create a partial Fourier series that approximates our data with coefficients defined by the real and imaginary components of the transformed values. So here's an example question from 2020. So this is kind of like a trick question. It looks like we have to compute the discrete Fourier transform, and it also kind of looks like numerical integration. But here we are integrating from 0 to 1. So if we actually integrate this part from 0 to 1, since k is an integer, we're basically integrating something like cos or sine, where all the positive and negative bits cancel out. So this part, once you integrate it, actually evaluates to 0. So we have integral from 0 to 1 of f of x dx is just this integral of a0, and that's equal to a0. Now we just want to find the a0, so what we can do is just find the average of all of these y values. So we find that that's 1 plus 2 plus 2 divided by 5. I'll also add in the zeros to make this a bit clearer. And that's just 5 on 5, which is 1. So this integral just turns into 1. The next example question is about the power spectrum. So the power spectrum is this graph here. So we want to express that in terms of the values obtained from the discrete Fourier transform. And this is given by the square of the size of those values divided by the number of terms. Then the next question wants us to interpret the power spectrum. So the claim is that this data has both yearly and monthly cycles of roughly the same intensity. So what this question is testing is, do we know how to read the power spectrum graph? So here it's cycles per year. There's a spike in 1, so there is a periodic component of so there are yearly cycles, so once per year, and there are cycles that happen 12 times a year, so monthly cycles. So these first two bits are supported by this graph. Now the last part is they're roughly the same intensity. So there we look at the height of these spikes, and we can see that they are pretty similar. So we can say that this is also justified by the power spectrum graph. Okay, so these two questions from the 2015 paper are kind of like, they haven't been tested again in any of the other papers, but what has been tested is just so the types of questions that have shown up are proving inverse discrete Fourier transform, and also just proving properties about this discrete Fourier transform. And the next example question we'll do is about the property of discrete Fourier transform of real values. So we want to show that half of the transformed values are just conjugates. And here, so remember we have, so we have the yk hat is equal to this sum of yj e to the minus I believe it's I to pi j k over n. Let me just check with this. Yeah. So we want to show that this is equal to the conjugate of this. So we write this as this sum, and then we can break the n and k into these bits. So after splitting this up, the term involving the n turns into this, and the term involving k turns into this. And then after a few calculation steps, we find that this bit is just equal to 1. So we are just left with yj times e to the positive of this bit. And since that's the conjugate of this part. And since all the yj are real, then we can say that this is equal to the conjugate of y hat k. Okay, now the next topic is, no, not the next topic, the next type of questions that get tested are inverse transforms. So here, generally, it wants you to prove the inverse discrete Fourier transform formula. So this So the steps are here. So we can start with this and show that this is equal to yj. So here we can substitute the formula for the discrete Fourier transform into here, and that gets us this. And then we can combine all of these into combine these two into one term, and after some rearranging we get this term highlighted in red. And the important thing about this term is that here, if j is equal to m, this thing is equal to 1. So let's call this thing kjm. So if we have j is equal to m, then this is equal to 1. But if j is not equal to m, this is equal to 0. So what we end up with is that all of these end up being 0 for m not equal to j. And when m is equal to j, then all of these will be 1, and there's n of them. So it will be n over n times yj, which turns into yj. So the main idea here is first switching these sums and producing a term that gives you 1 if you have that gives 1 if you have the right index, and 0 if you don't have the right index. And the final example we will do is the discrete cosine transform. So this is not a question. So this transform I don't think has been taught in the course, but in both the 2019 and the 2017 papers, I think this exact same question came up. And what this is testing is, like, do we understand the idea of how to prove the inverse Fourier transform. So what we did here, the key thing is creating this expression that evaluates to 1 if we have the right index and 0 if we don't. And they give us something like that here. And our job is to kind of produce that in here to find a expression for the inverse discrete cosine transform. So I think the process is actually quite similar to proving the inverse discrete Fourier transform. So let's say we want to find xn. Okay. I'm gonna take like a brief second to remember how this is done. Okay, so here we want to kind of induce this expression into our formula. So this looks pretty similar to what we have here already. So we can say, so we can multiply this term on and start from there. So we have yk times cos times this, and that's equal to the sum of xn times this bit I'm going to take screenshots instead, so it's faster than just writing. Oh. Okay. Okay. So once we get this, we want to make this look even more similar to this expression here. So what we're missing is a summation over k and a 2 on n. So we can just add the 2 on n in, and also the summation over k. And now in this expression, we want to isolate this term. So we can switch the order of summation and then get this. And then okay, yeah. So we get this bit, which is equal to 0 if m is not n, and equal to 1 if n is equal to m, if they are equal. So what this means is that here, if we have n that's not m, then that turns into 0. But once we have, if we have xm, that term will stay by itself. So this whole sum will evaluate to xm. And that gives us the inverse of the discrete cosine transform, which is the solution to this question. Okay, that brings us to the end of part 1 of this seminar. Thanks for watching, and tomorrow from 1 to 3 p.m. Part 2 will be on the same channel, and part 2 might actually be a bit longer because there's more content there, I think. Part 1 was a bit shorter than 2 hours. But thanks for watching, and hope to see you tomorrow.